Hey everyone, Frank on the board. We're really excited about this talk because it's something that probably a lot of you have been talking about your whole careers, but it's finally started to gain a little bit of traction, especially with the whole climate change conversation that's going on, how the built environment can kind of help solve the climate crisis, going beyond net zero. But so we have a few different people to kind of talk on the subject. We got Flax, the chief building official for Boulder County, Christin Whitco, the energy code coordinator for City of Boulder Planning and Sustainability, and then we're going to have Wil Srubar talk. He's a professor at CU. I'll let him do further introductions about that, but he's going to give a little presentation just kind of framing the conversation, what we're talking about here, why it's important, why we should care, and then we'll kind of go into more of the question, Q&A, discussion topics, and then you can kind of join in, and I'll just kind of chime in when I feel like I need to redirect. So, Wil, please come on up and do your thing.
Thank you. Thanks, Frank, and thanks everyone for coming today. So my name is Wil Srubar. I'm a professor at the University of Colorado, just down the road here. I teach material science and architectural engineering. I'm a structural engineer by training. I got my bachelor's degree from Texas A&M University. I went to go work for Walter P. Moore, which is a large structural engineering firm, around the time that LEED and the USGBC kind of took off and like wildfire in the mid-2000s. And as I went into practice, I started to ask questions about sustainability, what structural engineers are doing, and really the conversation was about energy, operational energy, making our buildings more energy efficient. And I really didn't get many answers as to what structural engineers can do. But I went further along in my education. I learned more about materials, materials chemistry, concrete, and how concrete is actually a pretty big problem in terms of environmental impacts, the way that we make cement right now. And so I was fortunate to land at the University of Colorado, where I kind of wear a couple of different hats. So of course I teach courses in structural engineering and materials and sustainability and life cycle assessment, how we quantify the environmental impacts of materials that we use. But I also lead a research laboratory called the Living Materials Lab, where we do some funky, crazy, kooky, Frankenstein-like grown materials, biomaterials for kind of way out there construction applications. That's the topic of a different little seminar. What I do want to talk to you today is about embodied energy, embodied carbon. Oh, I did want to mention that in addition to my role at CU, I also serve as the director of cement and concrete research at Katerra, which is a startup, construction startup out of the Bay Area. I lead a lot of their new innovative cement and concrete initiatives. I'm also, I'm hopefully a few of you have heard about the Embodied Carbon Network, but this, I'll have a little pitch at the end of what this is. But it is a now global organization of about 1,000 AEC and even policy professionals dedicated to understanding, quantifying, and reducing what is called embodied carbon in our buildings. So really the takeaway for today is I hope you walk out of here today being able to answer this question. Why embodied carbon? Why embodied energy? Really, what is it, first of all? And why is it important? Really, why is embodied carbon important, and why now? Why today? So because I am a professor, hopefully this will work, we're going to start with a pop quiz. All right. Little flashbacks to school. Classic problem. Which has the lowest embodied energy? Embodied energy is all of the energy that it takes to manufacture, use, dispose materials. Okay. We have some brave souls to venture a guess. Ceramic cup. Good questions. I had to clarify. And you submitted an RFI. Is this cradle to gate? Is this cradle to gate impacts, or what that's called a system boundary? Okay, cradle to gate meaning all the impacts associated with making it, and it's on the factory shelves ready for you to go buy. Okay, that's cradle to gate. Cradle to grave would be using it, disposing it, perhaps recycling it, etc. I'm going to say up to you to interpret for now.
Cradle to gate styrofoam cup.
Cradle to gate styrofoam cup. I had a vote for ceramic. But you bring up a good nuance because it totally depends. It depends, of course, on what the materials are, what it's made of, what it's used for. Okay, so all of these are used to hold liquid. How long will each of these last, and what we do with it after we use it. Okay, so if we were all born and handed a styrofoam cup, and that's the only cup we ever use forever and ever and ever, odds are that's probably the most sustainable thing up here. But we were always told that styrofoam is bad, it's really bad, right? We don't really know why it's bad. Hopefully I'll tell you. Hopefully you'll walk out of here knowing that. But really to answer this question, we have to quantify, put numbers to what is called embodied energy. So I already gave the definition of that. It is the energy that goes into manufacture, use, and disposal of material things. So I'm going to clarify the question for you. Cradle to gate. So what it is just made of. Okay. So what it is just made of, cradle to gate. Does this change anyone's votes? To quantify, what do you need? You need some numbers. So what if I gave you some numbers? What if I told you that the embodied energy of aluminum, raw material, is 155 megajoules per kilogram. If it's recycled, it's only 29. Stainless steel, 57. Polystyrene, which is styrofoam, 86. And ceramic is 10. What other information do you need to tell me with certainty what it is?
How many kilograms the cup is?
How many kilograms each of these cups is, right? The mass. So if I tell you that, the mass of each of these vessels, you make the quick calculation, you get total embodied energy. Lo and behold, it is the recycled aluminum can that has the lowest embodied energy. Shocking?
No.
We see a lot of these, right? Typically, energy correlates with cost, so this is probably cheaper to do, typically. Now, we assumed that the function of these cups was to hold 12 ounces of a room temperature liquid. What if I change that? Oh, by the way, congratulations, you just performed a very simple cradle to gate life cycle assessment. Hooray! Give yourself a hand. It's really great. It's really great. That may be the first time for many of you. It's okay. So congratulations. What if I change the function? So now I say each of these has to hold 12 ounces of 95 degrees Celsius, almost boiling coffee. What drops out immediately?
The aluminum can.
The aluminum can. I wouldn't want to hold that. We all know how conductive that is. I wouldn't want to hold that. So that goes out the window, right? It doesn't serve the function. So now, cradle to gate, lowest embodied energy is the styrofoam cup. It's proven. Okay? It's proven. One of the reasons why we're taught that styrofoam is so bad is not because of cradle to gate energy. It's because of cradle to gate emissions associated with making that styrofoam. We need a lot of blowing agents to make all the bubbles, and that has really high greenhouse gas, global warming potential because of the greenhouse gases that are used. In addition, if we look at the grave side of things, it's really hard to recycle this. So we just have to landfill it. And we have numbers that quantify the environmental impact of things that go into the landfill. So once we change the system boundary, then this kind of falls off too. But it all depends on what question we're actually asking. Now, let's bring it back a little bit closer to home. Which has the lowest embodied energy? Where are my A+ students? What did we just learn?
Recycled metal?
It all depends. It all depends. Okay? We're always taught wood is good. Okay, wood is good, but there are nuances with that. Wood is good, cradle to gate, because it sucks up CO2 from the atmosphere. We use it, but what do we do at the end of the lifetime? We typically landfill it, and off goes all the CO2 that it originally sequestered. So the lumber industry will say, oh my goodness, this is a carbon sequestering material, when in fact, it's really carbon neutral. Okay, so it just all depends. It all depends. But you can start to think, it all depends on the function of these materials. So a column carrying 100 kilonewton vertical load, you're going to use a different amount of wood than you would steel, than you would concrete. A glass facade with a U value of 0.5, a fixture that provides X foot candles, etc., or a whole building. Which is better, a wood building, a steel building, a concrete building? It all depends. You just got to put the numbers to it and make sure they all serve the same function. Formal definitions, embodied energy. Yes, question?
So there's a lot of people right now about mass timber construction.
Yes.
How legit is that statement? Because I'm guessing there's a more nuanced answer.
Yes.
If you have what's called a 3-story standard office building here in Boulder, and you have the choice of using steel, concrete, and glass, typical building package, or mass timber from an environmental point of view, do you think there's a clear winner? Or is it well, it depends if there's a plus and minus?
There's no black and white answer. It depends. Where is the CLT coming from? Where's the mass timber coming from? Exactly. How long is that CLT going to last? Will you make sure that it isn't landfilled for 150 years? There are a lot of nuances associated with it now, but I want to kind of muddy the water, but hopefully I'll bring it back to some best practices and good strategies. But one of those being transportation is really important. So if you're sourcing mass timber from Europe, let's think about that for a little bit. If you're sourcing mass timber from the new Katera Spokane factory that just opened in Washington State, that may be a little bit more reasonable. But it definitely depends. Yeah, other questions?
I would say that source of coming from Europe may not be as high as you think, because there's nothing lower, I think, than ship transportation in terms of its impact on.
It is true, but then it ends up at the Port of Houston and you have to then truck it or train it over, versus maybe that distance here in Spokane, it may be shorter. Who knows where it comes from? Who knows what the manufacturing energy is in Europe? So it really is dependent on the product. But fortunately, we're getting some really useful tools to help us make these design decisions that are a little bit hard to fully understand. So embodied energy and embodied carbon are the energy and associated carbon emissions associated with the manufacture, transport, use, and disposal of the physical materials. I'm not talking about building operations, running the thermostat, HVAC, lighting, electrical, not talking about that. I'm talking about all of the impacts associated with building material manufacture, use, disposal. So you can see that global CO2 emissions by sector, building materials and construction account for 11%. This is data from the Architecture 2030. Yeah, Architecture 2030, who have really been pioneers in making, crafting this message and making it really well known. Another statistic, over the next 35 years, 2 trillion square feet of new and rebuilt buildings will be constructed in cities worldwide. I think the metric is a new New York City. Every couple of weeks, a new New York City is built. What that means is that the emissions and energy associated with the materials matter more today than operating the building. Because this is over 50 to 100 years of the lifetime of the building. Over time, these obviously come more closer together. But if we are to meet climate goals set forth by Paris Climate Agreement by 2050, we have to spend time understanding this, reducing it, avoiding the emissions associated with the material manufacture itself. This, you may hear this term float around. This is what's called the time value of carbon. The carbon associated with burning coal to run energy just to operate buildings is less important than understanding where the energy and emissions are coming from to make materials. So, point of this message, materials matter, and they matter today. This brings up another point that I've made in my research called the passive house dilemma. Okay, so we all know passive house. Passive house means if you beef up the envelope, you can really get to net zero operating energy. Great, you save on your electricity bills. You don't have to turn on, you don't have to use anything from the grid. You can probably provide everything that you need on site. However, in order to get a construction like this, what do you have to do to the building envelope?
4 inches of foam.
4 inches of foam.
If I can interrupt on this, you don't have to use foam.
Correct. You definitely do not. You definitely do not have to. But if we look at, so one of the studies I did with my research group is I said, let's look at typical passive house construction envelopes. Okay, envelopes. And if architects and engineers were just to design a highly insulated envelope, they'd probably go look at case studies, understand what those are in terms of materials, and they may use them in their buildings unknowingly in some climates. Okay? What we wanted to point out is that perhaps if we use an envelope such as this, which has a lot of concrete, EIFS, which I forget what this stands for. Yeah, thank you. Structural engineer, not envelope designer. But and then we have polyiso, and we have some gypboard here. You can imagine that this is a pretty beefy envelope. And our hypothesis was that, you know what, in some climates, if you use this in typical residential construction, you're probably doing more harm than good in terms of total life cycle energy of the building. So we looked at 60 years of a typical residential house with each of these constructions. And we found, so these are each of the cases, each of those envelopes, and this is total life cycle energy in terms of the envelope and the operating energy, embodied energy in the envelope and the operating energy of the house over 60 years. And what we found, some things were pretty obvious to us. So in Los Angeles, where you're not really running the heating and cooling system, the typical low energy house, this is a low energy standard, actually we use the Boulder Habitat for Humanity, Flatiron's Habitat for Humanity construction as kind of a typical high performance house. You can see that obviously in LA, this is way over designed. And over the lifespan of the building, you are spending more energy in the initial construction to get that beefier envelope than you're expending over the entire life of the building. Right? So you're doing more harm than good there. And that was pretty obvious to us, or maybe not so obvious, but now we have numbers to back that up. Not so obvious were in other climates, Orlando, New York City, Minneapolis. We saw that some other just less beefier construction, and actually wood is good in terms of, and it is what we've also found, is that wood is actually good, and concrete not so much, in terms of total life cycle energy in these particular climates. So even this was designed on the passive house in the woods. You can look up that case study. It was designed for a climate like Minneapolis, but really something a little bit less designed could have provided less life cycle energy. Okay, so we weren't meaning to be exhaustive. We were just trying to prove a point that, again, materials matter, and passive house has been dead silent on this entire conversation, and for good reason. They're probably finding the same thing. Okay. Fortunately, they want to work with us in the Embodied Carbon Network to start to put numbers to it and really understand it. Okay. So it's not all doomsday, right? Because we give you some tools and best practices that even if you don't fully understand how to conduct life cycle assessments, that you can still not do more harm than good, but do good, period. So some of this is pretty ingrained in us already. Reduce, reuse, recycle. So be efficient with the materials that you have. reuse different materials. Okay, that's huge because you avoid pretty much all of the initial manufacturing energy and emissions if you can reuse materials. And we can quantify that. In fact, this is probably one of the things we can talk about. What we're working with the city of Boulder is to quantify avoided emissions if you reuse a building, or avoided emissions if you reuse steel. Buy local, specify carbon storing materials. So I would personally say wood is a good choice if it's properly managed throughout the life cycle of the building. Okay? If you're not using it and landfilling it. So things like formwork, probably not so great because you use wood formwork a couple of times and you landfill it and throw it out. So just be cognizant that if you're using carbon storing materials, you need them to last long enough so that they don't release their emissions in the short term. And then, if any material ever rings bells in your head, it's concrete. Okay? Concrete is the second most consumed material on Earth after water. Okay, that's pretty shocking. Cement, so the powder we use to make concrete, is responsible for 6% of our global CO2 emissions. It's also the most expensive ingredient in concrete. So no brainer, if you reduce cement without compromising fresh and hardened state properties, you're going to save on cost and you're going to save on carbon emissions. The best strategies to do that is to incorporate high volume supplementary cementitious materials like fly ash or slag. Some of you may be familiar with that. Yes? If they are vertically integrated, and I'd be happy if there are any cement and concrete folks in the room. What I have found, if they are vertically integrated, like the Cemexes of the world, the Cal Portlands of the world, if they are making cement, they want to sell you cement. Now, you could be smarter and savvier, and there's another reason too, because sometimes high volume fly ash and slag mixes don't finish properly, so folks just get annoyed with how finicky it is. But we have seen, at Katerra, we have seen in upwards of 50 to 70% replacement of cement without compromising fresh and hardened state properties. And it's just a matter of training and educating the finishers on how to do that properly.
So much going on in terms of additives to cementitious materials to improve their performance, quality.
Yep, so.
What are the environmental impacts of those additives?
Yep. Yeah, that's a really great question. So the fly ash and slag are byproducts of coal burning and steel making. So they're not going to be around forever. In life cycle assessments, the concrete industry takes into account none of the impacts associated with fly ash and slag manufacturing because it's technically a waste product, and if the concrete industry didn't use it, it would just be landfilled. Okay? The great thing about those materials is it makes the concrete better and more durable, and it lasts longer. Okay, so they're really good materials. We use them for a good cost reason and a good durability reason and a good sustainability reason. There are other additives. So you can start asking Martin Marietta for Portland limestone cements, which replaces about 5 to 15% of the cement with ground limestone. And we've shown, well, the cement and concrete research community has shown that it doesn't compromise fresh and hardened state performance, and you immediately reduce 5 to 15% of your carbon emissions, which is great. There are other blended cements that use other mineral admixtures like metakaolin, like a calcined clay, which are mostly available in certain regions of the country. But what we have found to be most successful is that, do we have any structural engineers in the room? Folks that work with structural engineers. 28 days strength, right, is the magic number that we build with. 28-day strength. Why? It's an outdated convention. Back in the 1920s, people did a lot of concrete testing, and they were like, yeah, concrete pretty much reaches its strength around a month. So we specify 28-day strength. What we know about concrete today is that it continues to gain strength over time, and we can rely on things like 56-day strengths or design to 90-day strengths so long as it doesn't significantly impact the construction schedule. So I've really pushed at Katerra to specify in our general structural notes 56 or in some cases 90-day strengths. So you can imagine reaching 2,500 PSI or 3,500 PSI at 90 days is not that hard to do. Yes?
I mean, theoretically, if you're using that model of calculation, you can use less concrete. So if you're making beams, making a much smaller beam,
Bingo. Or you use the same size beam, but a different mix that has way lower cement content. Yeah, bingo. So I teach entire semesters on cement and concrete, so I digress. But I think this is a nice slide because it leads into more of the discussion points, and I have some resources on the next slide. But to really wrap our head around this idea of embodied emissions and embodied energy, it really is, we have to really understand material quantities. Okay? We really need to know how much material we're using. And at the design stage, that's really hard, right? Because things are iterative. As a structural engineer, you start with a 12 by 12, you may move to a 12 by 16, whatever size column. So in the design stage, it's a little bit iterative, but really material quantities. If you know quantities, and we can look up all of the coefficients of the embodied energy, embodied carbon coefficients, we can just do that quick, simple equation, multiplication, and get at the total environmental impacts of the materials themselves. That relies on data. So, okay, what is the embodied carbon per kilogram of, I don't know, aluminum or vinyl siding, right? Vinyl siding. That requires a lot of data. Okay. Fortunately, there are databases that are being built for us to use, so we don't have to go out and do the calculation for us. There are databases that are being built, tools and software that are being launched. So some of you may have heard of Athena Impact Estimator for buildings. That's a good one. Tally, which is a Revit plugin. So if you have a Revit model, you hit Tally or one-click LCA, and it'll kind of tally up all of the environmental impacts of your materials and show you where the hot spots are. Guaranteed it's going to be the concrete. It'll definitely be the concrete. If you're deciding on what carpet to specify or what to put into your building, material manufacturers are creating what are called environmental product declarations, which are basically nutrition labels for all building products. Martin Marietta has one for every single one of their concrete mixes. Guaranteed. Guaranteed. Because if you're going after LEED certification, then one of the categories of points in the materials resources, or one of the credits in the materials resources category, is a life cycle assessment, a whole building life cycle assessment. And you have to show that you're kind of making design decisions that lower the environmental impacts of the building. So they have those ready to give to you if you ask for them. So that helps you make some decisions. So there are databases of environmental product declarations. Again, pay special attention to sourcing and transportation. Where are these products coming from? Many EPDs are cradle to factory gate. Okay, so Owens Corning will say, yeah, this product, this is all the emissions and energy that went into this, but I don't know where it's going, so we don't report it. So just pay special attention to that. So new materials and certifications to use those in buildings. I mean, we've all heard of hempcrete, right? Right. So you take the stalk, the hemp shiv, the shiv of the hemp plant. It's really woody. You crush it up. You mix it with some gypsum. You dry it out. It's a really nice insulation material, and it's non-combustible. Europe is using this all over the place. We weren't able to cultivate hemp in the United States until 2014, I think. We all know that. Here in Colorado. So this, I think, is a really good carbon storing material. Hemp grows really fast. And then these low CO2 cements, so high volume fly ash mixes. Also alternative cement chemistries that are coming on the market. So I'm really paying attention to Solidia. I don't know if any of you have heard about Solidia, but they're kind of this new cement company. I think this bleeds into a little of the discussion that I think we'll have now is policy mechanisms for low carbon procurement, policy mechanisms for material reuse, mandating that, and then the LC and carbon resources I can show at the end. And I think this is a good kind of transition point. I'd love to invite my fellow panelists up to kind of chat a little bit more. And then I have a note about as they do that. So I will be the chairman of the Architectural Engineering Institute Conference in 2021, which will be held in Denver. If any of you are interested, there's going to be an LCA track, like an Embodied Energy and Carbon track in that conference. If any of you are interested in just being on a local steering committee for hot topics in the industry, or you want to get a little bit more involved in that effort, just shoot me an email. You can find me online, no problem. So I think we'll transition a little bit and go back.
Oh,
Yeah. Thank you. Yeah. Yes. So it's just my first initial W and then my last name Srubar. It's a doozy, I know. Eastern European. What's that? Yeah. At colorado.edu. So WSRUBAR at colorado.edu. So CO2, we use CO2e as the metric. So everyone knows megajoules or BTUs, or what have you with energy. For carbon emissions, we use CO2e. The E stands for equivalent, because there are a number of gases that are greenhouse gases that have global, what we call global warming potential. So we just convert all of those different amounts of the gas to a carbon dioxide equivalent. So for example, if 1 kilogram, compared to 1 kilogram of carbon dioxide, methane, which you probably know to be a really bad greenhouse gas, has 25 times, a kilogram of methane has 25 times the greenhouse gas potential as carbon dioxide. But we just do a little metric conversion to lump it all into one that encompasses all of that. So other ones are like the nitrous oxides, the CFCs, so the chlorofluorocarbons, the refrigerants, and things like that.
Well, so since we're having this larger conversation, and supposedly we think it's important, hopefully now, the real question is like, well, how do we make it happen, right? We make better materials choices. We as some designers or engineers in the room, maybe you're making choices. Hopefully you're able to utilize some of these resources to, find out what the, embodied carbon are of the materials, do life cycle analyses, things like that. But on a greater scale, where do municipalities come in terms of either regulating or incentivizing? What are some different municipalities around the world doing, especially ones that have potentially declared a climate emergency? What are their plans? And I know, Christin, you can probably talk more about that, what Vancouver's doing, what Boulder's doing, and things like that.
Sure. Yeah, so first I just want to say thank you to Wil. It's amazing to have a national expert in our backyard. So I look forward to working with you more. We've started to partner with Wil on other city projects. He mentioned the Alpine Balsam project where we're taking the hospital down. We're reusing parts of the hospital site, and then we're also deconstructing at great cost and really using it as a tool to learn how to take buildings down when you actually do have to take them down, because not every building can be reused, or they do get to the end of their life cycle, and so deconstructing it in a way that makes sense is something we're learning with him as well. So Boulder, as Frank mentioned, we declared a climate emergency as Vancouver and many other leading cities did this summer. And so now we're kind of recalibrating our climate action plan, and the circular economy piece has really come into play. And as we look at all of our goals again, figuring out how to break the linear economy and making it more of a circular economy. And this piece, the embodied carbon piece relative to the built environment, is really an important thing that we're working to figure out. And I think that's really what I'm here to learn more about, is really what is the city's role, what is the county's role in setting policy, or how do we help you guys, the designers and the builders, get to buildings that are low embodied carbon? Is it policy we need to create? Is it incentives? Is it financial mechanisms? I think that's what everyone's really trying to learn. The city of Vancouver has set a really lofty goal a lofty goal of saying that all buildings by 2030, I believe it is, will be 40% less embodied emissions than their current buildings. So they've sort of set this lofty goal, but then how they get there, everyone's trying to work that out, and I think we're all in the same boat of working on that. So it's great to get in front of all of you and pull feedback out of you as well.
So I guess I wanted to just start by saying that how completely frustrated I've been with this topic for decades now. It's absolutely infuriating. Sure. Yeah. So I've just been really frustrated for a long time about this topic. There's very little that in this industry that is filled with such an unbelievable level of confusion and uncertainty. Even things as simple as CO2 equivalents, right? We talk about converting methane to CO2 equivalents, but that calculation, that 21 times, that's based upon an assumption of what lifetime, what time frame you're doing that equivalency across. Are you looking at it over a 50-year, 100-year, 1,000 years? I don't know where that equation comes from, but there's an assumption built into that that tells us, well, which is better, methane emissions or CO2 emissions, and by how much? How do these things compare? We can't even answer that simple question without putting in these extra layers of caveats about what we're really talking about. When you try to say, what's the embodied energy of a building, the number of uncertainties is a longer list than anything else about the building. I mean, it's astounding, and I think it's really easy to get to a point of paralysis because of that information. You hear one thing from one thing, you get one thing from something else. This clearly is a product that costs a lot more, and you're going to try to justify that to your client, but yet you really can't hang your hat on any of the numbers anywhere in there. So that has been incredibly troublesome. It certainly is the kind of problem that makes it really hard as a regulator working for Boulder County to create regulations that tell people how we should behave and what's that based upon. It's really challenging to get there. When we talk about the operational energy of a building, that's much more straightforward. We can actually quantify that in a much more precise way. There's a lot of nebulous information here. Now, that said, there are certain things that we can rely upon with certainty, which is smaller things tend to consume less energy than bigger things. Things that last longer are better than things that don't last longer. Things that don't have health impacts are better than things that do have health impacts. One of the things that's not in any of these equations, we talk about the styrofoam cup. So you can talk a lot about the CO2 and the energy that goes into those, but they're part of the problem of plastic foam insulation is that there are chemicals involved with those materials that are very toxic to human health and animal health and ecosystem health. Now, those costs are very hard to quantify, but they are extraordinarily expensive. If you want to look at a carbon-intensive industry, look at our healthcare industry. There's just a huge amount of environmental impact that goes along with human health, and that's not in any of these equations. So I guess what I keep coming back to is okay. So when we look at a wall package, for instance. There's a general rule of thumb that I find myself thinking about, which is the thinner the wall, the more energy intensive it's going to be to get a similar R value. With the extremes being things, very thick wall assemblies like straw bale or adobe or cellulose that have a low R value per inch, but they tend to be really big assemblies. And at the other end, you can get vacuum insulated panels, which are super thin, but incredibly energy intensive to make. So the thinner I'm trying to make those walls, the odds are I'm making that wall assembly more carbon intensive than it would be otherwise. And so I have a hard time, I really applaud the efforts of the academics to try and get us out of this morass that's caused by our lack of actual information. But we really need these answers, and we need them now. But as a practitioner, I'm like, okay, I'm left with this question, what do I do? In general, the idea of particular products that are very expensive, usually that cost is a proxy for the carbon intensity of the material. In general, things that cost more are more carbon intensive than things that cost less. Now, the specific examples that change that equation. So when you look at something, again, like the plastic foam insulations, they actually are relatively cheap compared to their environmental impact. And fuels are also, they don't behave that way. But for the most part, we can kind of use how costly something is as a way to estimate how carbon intensive is this material.
I'm curious, has anyone here done any life cycle analysis or looked at the embodied carbon or an EPD or any of, I'm just curious how much traction there is out there. Some of you. And where is that coming from? Is it client driven? Is it personal interest? Is it
Research.
what's that?
Mostly research driven, not client driven.
Not client driven.
We're starting to, through like programs like AI 2030, we're starting to do data entry, things along those lines. But science it's still out there. The results are still out there.
Right.
If I enter information for a current project, I'm not necessarily tracking its life cycle.
Right.
Costs of the amount of what policy taking place.
One of the things that I think about is a presentation from Red Pepper Design a few years back, where she was talking about the granite countertops. And for a while, that was considered this environmentally friendly material. You can put in the granite countertop, and it would outlast all the other materials. It would keep going strong. But one of the things that she said was that except people get tired of it after about 5 or 6 years. And so if we're tearing it out, then in fact you would have been better off with paper mache from an environmental point of view, because you weren't using the benefit of that long-lasting durable material. You're churning through it, and if you're churning through it, then it's clear that that's waste, and that waste has an environmental impact.
It has been one of the big questions recently. Should we be designing buildings to be essentially mark-acre houses, which are easily deconstructible? They were only designed to last for 50 years because we know that the technology 50 years from now is going to be completely different from what we have now. Should we actually be designing houses that are intended to last 200 years? When, especially if we're gluing it all together with foam insulation, that we've essentially created something that has an end of life and it's done, versus something that
Designing for
reasonably easily deconstructed, repurposed just 50 years from now when we want a better way of doing it.
Yep. You get that. Yeah.
The latest trend, the designing for disassembly. Certainly with city projects, we're thinking about that more and more because we do so many tenant improvement projects. To be able to disassemble and reassemble to your new configuration that you need is really an important part of. There's a whole circle. Designing for disassembly. Speccing materials that are low carbon to begin with, and minimal. Carefully selecting your materials to reduce the amount of carbon that goes into what you do build. Ensuring the operational energy gets to net zero, so on the operation side you aren't taking a hit, and then making things reconfigurable as much as possible, and then ultimately when you hit that end of life cycle, disassembling and reusing at the highest quality possible, rather than recycling the steel, actually taking the steel out and finding a new home for it, rather than, everyone likes to use recycled steel, but if you can actually reuse the steel, that's really your first priority.
Yeah, there's been a huge effort locally to really work on the operational energy of our buildings, and it's clear that we know how to do that now. We can build buildings that have very low operational energy and maybe even net positive. However, if we're doing that by prepaying 30 years or 40 years of carbon, so when you walk through the front door the first time of the building, all that emissions is in the air. Well, I talk to my atmosphere scientist friends, of which we have many in this community, and they say, wait, no, we're too close to too many tipping points. The carbon emissions today is actually a bigger problem than 30 or 50 years from now. We need to be thinking about making low operational energy buildings today that don't have that bump of emissions by the time you walk through the door the first time.
Are we prepared to sacrifice some of the operational regulation that we've created in order to move essentially backwards?
From a policy perspective, I think that would be a reasonable approach.
Are we prepared to do that?
I think the problem is that because the embodied energy is so hard to pinpoint, I'm having a hard time figuring out how to regulate it.
How you can demonstrate. How you would demonstrate that overall you're doing the right thing. And that's the policy end of it is really tricky.
You know, the operational energy, you know, we use, you know, for Boulder County, residential construction, we use HERS ratings to tell us whether the building meets the code or not. I don't have anything even approaching that from an embodied energy perspective.
One of the, just a really quick comment on that. So, you know, the NREL, right, we have a huge legacy of energy and even renewable energy. And for building designers, especially in the commercial sector, we have these model buildings, these commercial archetype buildings that tell us what an average EUI is according to ASHRAE 90.1, et cetera. So my group and a couple of others are starting to do the same with embodied carbon to say, you know what, an actual single-family home, embodied carbon is and just looking at core and shell and foundation, is about, it's definitely less than 500 kilograms of CO2 equivalent per square meter. Okay, and then you can make the calculation into what that means in terms of square feet. You can imagine like that is on average, and it is up for debate. There are a lot of nuances with that. You brought up a point about, you know, data, like where does the data exist? And I think in the last 5 years, the databases that have been built have given us more of a crystallized view of what it does take to make glass, wood, steel, carpet, et cetera. And the EPDs that are coming out of material manufacturing plants now are just, it's overwhelmingly astounding. It's really great. But again, that's just cradle to gate, which is what matters now, right? Cradle to gate is what matters now. So I think this is a great time for this conversation too, because it's just enough traction to get going. One of the policy, I guess more of the policy traction examples I have has to do with Marin and Alameda County in San Francisco. I was part of an advisory panel, kind of advisory board that crafted language for a low carbon concrete specification for all municipal buildings in Alameda and Marin counties. And that just went out for ballot. I think it passed last week. I need to double check, but there was really no objection to it. What that did was for every type of, it set limits on cement content for different compressive strengths of concrete. So it forces the hand of the supplier to give, for all city projects, to deliver low carbon concrete. How they get there is there's a couple of pathways, but this is something that we've talked to Christin in the city about.
It's those moves that are really exciting, I think. I think it's a really complicated topic, but I also think there's some really simple low-hanging fruit that everyone can start incorporating. That's
so for concrete under LEED 4.1, what are the differences for reuse and recycled materials in concrete? Can you do reuse concrete?
You get more points
you
for
gotta
reuse.
crush it down and then put it in as aggregate. Does that make it recycled? Or do you have to have the entire wall or square footage of stuff that is not ground up or otherwise tampered with to make it recycled rather than reused?
Yes. So the definition of reuse is reusing the same element as in a similar application. So a good example is like a steel beam, a steel I-beam. You may have to truncate it because there's bolts, there's connections on the ends, but you may need to truncate it, but you can use that entire element, reuse it. Whereas if you recycle it and you reuse crushed up concrete now as aggregate, it's not a direct reuse, it's a recycled application.
So I have a question on a policy scale. So we have, HERS ratings, we have floor door tests, we have energy audits, those sorts of things. We can do energy modeling. So using under that similar framework, in this whole chicken and the egg conversation where we decide, okay, maybe we have a regulatory body say, well, we have to do, or maybe you get some sort of break or tax break or something if you do a life cycle analysis. Now, does that in any way put pressure on product manufacturers to get third-party analyses done on the materials? Like, how do we make progress on both ends of the scale, and which one happens first? You know, because we're kind of in this, like, there's energy, but it's mostly on a side where it's a little bit more, it's not regulated, it's not incentivized monetarily necessarily, it's more just out of the kindness of our hearts because we care about climate change. So how do we force hands a little bit more?
I mean, that's clearly been effective
already. That's why we're, in terms of the life cycle assessments that are available from manufacturers, that's how we got here. The LEED program had points that were awarded for having those documents, even if those documents weren't being used for any particular purpose. And so that was getting people, design teams, to request these things from manufacturers. And that requesting eventually led to more and more manufacturers doing this. And then once you get to a critical mass, now you can require it. So you know, it is having an effect. It's just, it's complicated and it's slow. And to be honest, with the manufacturers, it's really vulnerable to gaming because each new product category can define their rules. Each one tries to define in a way that makes their material look advantageous, and so you get, you know, the concrete industry and the steel industry and the wood industry sort of all competing for the same marketplace, all trying to spin things to make their particular product look better. And those disagreements about how it should be structured make it really hard for the user to really get a good apples to apples comparison when they're just saying, I need something structurally to span this space.
But I do think that's the policy roadmap. I think it's basically starting to require life cycle analyses, not requiring a limit, you know, not saying the 500 per metric, you know, what was the
square meter?
Square meter, right? Yeah. But just as a starting point, requiring the analysis so that we can start to see those come in the door, see where buildings are landing, and then to start to regulate, you know, where should the buildings be landing, and then start to ratchet. Just like operational energy, you know, we required the energy model, and then we required you to be so much better than the baseline building. I see the policy roadmap for embodied carbon taking a similar path.
Given the complexity of all this, and certainly when you start to get into the details, it seems like there's just lots of headaches, and certainly when you're talking about a single family home, you know, potentially adding a lot of cost to do that type of analysis. To your point, Ron, like, given that cost is partly, you know, reflects embodied energy, and then I'm just wondering, if we zoom out, are we better off looking at a carbon tax?
Yes. Unequivocally. Absolutely.
And like really putting our effort there, because it seems like that just kind of takes care of it.
This is where building scientists and economists agree every time.
I've never met anyone who studied that who didn't come to that very conclusion, that a carbon tax is the way to fix this. And that's been known for at least 15 years that I'm aware of, maybe longer.
And I imagine that that's not possible at a county or a state level. Is that really only possible at a federal level?
Washington State has at least, there's been some movement in their state legislature, but nothing has manifested itself yet. That's the only example that I know of.
For to
all
really
your
be,
Congress,
yeah.
people,
I mean, for really to be successful, you kind of want it to be across the entire economy. That's the way it's going to work the best. Is if not talking about a particular material or a particular industry, but just having it across the whole system. That's gonna work. If you just try to do it in one city but not the city next door, I don't know how that would work.
But we have lots of regulations in Boulder that are just for us to push things in a very particular way. I guess I don't quite, like, it seems like your fees for building permit could be tied to your part. I mean,
so for instance, right now, in Boulder County, I have an obligation given to me by the state of Colorado that says I have to have an energy code. I must regulate energy. If I have a building code, I have to regulate energy. It doesn't tell me details about how to do that. It just says I'm required to do that.
it doesn't even give me permission to regulate embodied energy. And I had some meetings about this a while back. If there's actually one statute, if we could squirt the word embodied into a particular place in the state constitution, I'd be all set and up and running. But I haven't been able to get that. So
Lauren might have a point. So in the city of Boulder, if you're being annexed in, they have doubled the inclusionary housing fees, doubled the tax. There's a new subdivision or street up in North Boulder where they put in a special language, which I've never seen before, which says that your inclusionary housing fee is proportionate to the inverse of your energy score. Have you seen this yet? As your PERS rating goes down, your inclusionary housing fee goes down. I've never seen that. It's awesome. It's the Vine Street. And that, just as a mechanism, so if we're talking about a local carbon tax and then doing something locally, perhaps it can be an offset to the various fees that the city and county can charge for the building permit.
Yeah, I think a life cycle assessment could be. A carbon tax would be too far reaching, but certainly a life cycle assessment is something that we are looking at, how to incorporate that and in an incentivized way, the carrot rather than the stick in terms of how it gets rolled out.
Yeah, if you're going to have them do some sort of analysis for embodied carbon, that you would have them do a complete life cycle assessment and look together as well. There's some issues with ozone and how much of an impact today's finishes and materials have compared to other things that are illegal in this country.
Yeah, I will thank you for bringing that up. So if you're familiar with LEED, there are 6 major categories. Today we just talked about 2 of them, energy and carbon. There are other categories like ozone depletion potential, acidification potential, eutrophication potential, and smog formation potential that LEED requires you to report. If you use a software like the Athena Impact Estimator, it does all of the calculations for you. It also does human health particulate, I think that human health particulate categories and a few others. But for structural materials, I'll make 2 points. Embodied carbon arguably matters more because as we integrate more renewables into the grid, okay, embodied energy may in fact go down. Okay, if we just think about if all of our energy is coming from solar, it doesn't matter how much, there will be no coal, so the embodied emissions and global warming will not will be curtailed. However, there are some materials that are manufactured, like foams and cement, that give off greenhouse gas emissions no matter how you get the energy to do it. Okay, it's a chemical thing. So that's why, I know this topic is really about embodied energy, and there probably is a good entry point with being from Colorado, being in Colorado, having that leverage of like, we care about energy and then sneak it in. But, that carbon piece is really, really important. And this global, I like this comment too about do we need to wait for the global consensus? And that's what the Paris Climate Agreement, that was our chance, right? But of course the US said no thanks. Well, one person in the US said no thanks. But there are these other municipalities that have stepped forward and said, no, like we want to do something and still achieve those goals. So.
This question actually kind of dovetails in terms of operational energy, but also I'm in the solar industry, and what we've seen a lot of commercial buildings struggle with is that the property tax increases in direct proportion to the kilowatt size that they just installed for solar. And so they're ticking the boxes and getting into energy code compliance, but looking at embodied energy, this is something where we're a SunPower dealer. We like them because there's a life cycle thinking behind the manufacturing and the recycling at the end of useful life. And that I see such an incentive of eliminating the property tax if you have the life cycle analysis on the actual panels themselves. Is that something you guys have ever tried to look at? Because this is something where people are trying to get into code compliance, but then at the same time, their assessment increases and they just you know, that chews up into some of the gains. And with everything else going on in the solar industry, with federal tax credit going down, it's going to be diminishing unless we do something, unless we extend ITC or think of it in ways like tax. Is that one way that could be incentivized?
Yeah, I mean, it's worth pursuing. You raise a really good point. I mean, there are sort of perverse incentives all over the place. You know, like tipping fees are cheaper than recycling fees. You know, they exist in a lot of places. That's an interesting one. That's worth looking into. We should connect afterwards, and I can at least give you some concrete answers as to yes, we could or yes, we couldn't.
I was at a conference last week where it was stated that 25% of the cost of building was in all the regulation part. And that wasn't in Boulder, okay? I suspect ours are higher. I mean, if you tell that to somebody who's building a house, Scott, say, you know, I can build your house for this, but here's what it's costing for these other things. I have thought all of this, and some of you know I've been around this for a long while, but somehow we have to get this under control, because we can have all the regulations, we can have all the other things, but we're forcing people to rent, to not build, to do other things. And we talk about life cycle. They've had long life cycle on buildings in Europe for a long time. We consistently build stuff to last 35 years. There's a disconnect from it. I wonder if we're not chasing the wrong thing.
Well, when I hear studies like that, the first thing that comes to mind is, well, what are you comparing it to, right? You know, a single-family home that's built to the 20, and it was, you know, so carry the 2015 I codes to what, a tent, a place that has no building code. So that comparison is always a little bit funny in my mind when you say it's more expensive because of the regulations.
Association in Colorado, you get the
Yeah, right, but so often when you dig into those details, the question is, what are they comparing it to, right? I mean, you know, we don't want houses falling down every time you get a freak big snowstorm. So there's structural requirements in the code, and those are there for good reason. It's clear, no matter how you slice it, though, as we make our homes more and more expensive, there is an increasing emissions associated with that directly, and that's a problem, as well as the affordability of housing. That's also a problem. So if we have people, you know, so and we also, you know, have this funny thing locally where as we make our regulations more and more restrictive, we push people away from this area, and then they're commuting further to get back to where the jobs are now. So you haven't really solved it any way you've sliced that. It's clear that we need to be looking for solutions that in fact are affordable. You know, often when you do an analysis of our community compared to other areas, what you find is that our houses are considerably larger than other areas. You know, the average house size in this country is, I think, around 2,600 or 2,700 square feet. We're way more than double that locally. So that's part of the problem as well. We also, you know, we have large lots with large houses that are expensive, and you kind of really want to solve all those at the same time. It's clear that if you compare that to the overall emissions of a community that has smaller homes on smaller lots that are closer together, then that from an environmental perspective, that's better. But that's not necessarily the way our community wants to develop.
It evolved, and you know, this was in the country of the sticks before a lot of us came here, and so they weren't thinking about these kind of things. But I see this for us in business as a major issue if we can't figure out how to get control over all the stuff we want to put into it because we want to feel good, and yet people can't afford to be here. I mean, you know, it's unfortunate that I represent the major part of the population in this city anymore. I'm headed a lot closer to dying than being born, for sure. So that's a bad place to be, and some of this has been the result of it. Most of you probably don't have many of your employees that are even able to live in the city or be here. We've got to tackle this together, not just with more regulations. And as you know, Ron, from the whole energy interest in conserving, it's inverse to where the money is. The people with the least money are the most interested in it. The people who have the money don't really give a You see this stuff, they want to feel good, and you guys are not into it, but it's not typically their driving passion.
Yeah, I mean, you know, we are living in a wealthy community that has a lot of embodied impact. You know, I mean, there's this myth that you can have sort of a high income, low carbon lifestyle. And that really doesn't exist. If you're earning well and you're contributing that money into the economy, there's a carbon footprint associated with that. If you look at you know, that was one of the things that was really interesting in some of the international climate negotiations, was that really some of the most powerful and impassioned pleas came from communities that had very underdeveloped communities that have had very, very low emissions. Their emissions are you know, much smaller than the developed countries, yet they were feeling the impacts more directly. So it's clear, you know, you can't just solve this by layering on regulations to an affluent community. You need to go a little further. Now, what's interesting about some of the stuff that we've done, not all the stuff, but some of the stuff that we've done, and by way of regulation, has informed other communities elsewhere and has informed thinking. You know, when you think about just things as simple as doing HERS ratings, you know, and doing below door testing, that was something that was a really boutique, high-end kind of consideration a while back. But there's been a proliferation of that, even in communities that maybe are less affluent. That training, that field work, that learning, that expertise was borne by the more expensive communities, and that has trickled down. I think the same thing happens with LEED. I think that the projects that pursue LEED certification have this ability to inform all of the, not just the owner and the occupants of those buildings, but all the trades that worked in those buildings, all the material suppliers that supplied materials to those buildings. And they learn something through that process, and then they can apply that learning to more affordable projects. So whereas it used to be that only really high-end custom homes were the ones that were doing air sealing, now everyone knows how to do it. It's becoming you know, a commonplace because it's not that much more expensive. The expensive part turned out it was the education. It was teaching the contractor community how to use the right materials in the right sequence to make a tight house.
I would say they were forced into doing it by regulations. Okay, in other words, what happened here is people say Boulder is great because the regulations have made us much more energy efficient. I do not think it would have happened without those regulations. But I think the other side of it is people become less excited, less disciples, because it's just part of the system. We should have more people doing what you did on your home. Seriously. I don't know if anybody else has gone down there and done that, but you were a leader.
I'd like to see some more incentives rather than trying to rely on regulations, which is more like whatever you can get away with crowd. You know, maybe just requiring that a life cycle assessment be performed, not, you know, what you're doing with it, and then incentivize bringing that down from a baseline, perhaps. So there's a lot of uncertainties in the databases right now for embodied carbon, and there's not a big consensus about it. So in dealing with those uncertainties, more so from an incentive point than a regulatory point of view, I'm wondering how you might feel about comparing those uncertainties to the uncertainties involved with RECs, not carbon offsets, but RECs. And in Canada, they have embodied carbon included in their net zero program, but you can offset your operational energy and your embodied carbon with RECs. So how do you feel about the uncertainty with RECs compared to the uncertainties in the database for embodied carbon?
I can't speak to that very well.
It's an interesting question.
Yeah.
In the 2021 I-codes, which people are voting on this week, there is a measure to say that you can't count a renewable energy system towards your HERS rating if you've sold the renewable energy credit to that system. I don't know if that's going to be passed up or down. But it's kind of an interesting question that they're actually looking at on a national level. Is, you know, if you've sold off the RECs, it's still reasonable for you to claim the environmental benefit of that solar system on that home.
Do you think that the uncertainties in the databases for embodied carbon are greater than the uncertainties for RECs?
I don't know if you can compare them one to one.
That's a hard question to, that would be a hard question to answer.
Yeah, so in Canada, they let you offset your embodied carbon, right?
When we start talking about the life expectancy of these different materials, do any of you have any opinions of all this preaching about carbon sequestration? And I'm wondering if it's kind of a joke or not.
For wood products or mass
Mostly for wood.
I can speak to that a little bit. So if you use a software to calculate your environmental impacts of the building materials, there are some inherent assumptions as to how long certain products will last. So like how often you need to replace the carpet, how often you need to repaint different walls. And there are also assumptions built in as to how long structural materials will last, like wood, concrete, steel, and what happens at the end of the lifetime. Since Katerra has come out of the gates with the CLT mass timber factory, one of the things that we've really focused intently on is paying attention, even though we're selling CLT and we're building CLT buildings, is paying attention to the anticipated second life of the product. So we have a concept that we came up with, and maybe some of you are familiar with this concept of buildings as material banks, and that we should actually be inventorying all of the materials that go into new construction, so that if there's planned deconstruction, that we know where the material resources are. So we've thought about born-on dates for our CLT and a do not landfill by date for our CLT to ensure that the carbon that we store, we can count toward a biogenic carbon sequestration. That requires, again, kind of consensus on the industry to do that. But as a general rule of thumb, you can count on any wood or woody biomass products like cellulose, insulation, to have sequestered the carbon cradle to gate and for a couple of decades. Okay, but this idea of even aesthetic obsolescence, where people come in and they're like, I don't like the way this looks, I'm going to throw out all my wood cabinets, or the MDF board, we technically don't have control over that. But if there is, again, maybe some other initiative that says, well, there are do not landfill by date, so we have to keep them in this circular economy within the community, that is, I think, the best ideal scenario.
Did you just coin that phrase, aesthetic obsolescence? I like that.
No, it's a thing. It's not my nerdy research. Yeah,
that's a great term.
Like functional obsolescence is when something breaks,
right.
But aesthetic obsolescence, and then technological obsolescence is just us all buying the new next iPhone because it's the latest and greatest. When the old one, I still have like a 2000 or like iPhone 6 or something. It's a brick.
So we only have a couple minutes left to kind of get back to what we can do in the meantime. And you were kind of touching upon this now, where it's like, okay, well, what are some basic themes that we can hold when we're designing our buildings? Like, okay, so we know the most embodied energy in the building is probably in the foundation, the building envelope. So, like, are we trying to reduce our concrete? Are we trying to use cellulose? Are we talking local materials? Are we talking agricultural products? I know the chain goes really far. You can go down a rabbit hole. It so depends, but like, what kind of I don't know, lay out some sort of pathway for us.
It reminds me sort of the food stuff. Like, I think Michael Pollan with his eat vegetable, what is it? He has boils down nutrition science into 6 words.
Eat real food.
Yeah.
Not too much, mostly
Mostly
Thank you.
Not too much.
Yeah, do you guys have anything to kind of leave us with? Should we just do double walls of cellulose? What are we talking about?
I think things like building a little bit smaller is a universal win-win. I think using less fancy materials is a good idea. Using less toxic materials. So don't do a lot of foaming your house together with spray glue or spray foam insulation. Using materials that the natural materials have a pretty good life cycle, not just because they're made from cellulose, like cellulose insulation or wood, but also because we understand what that life cycle is going to look like. We understand how to turn it back into compost. So the further we get away from those systems, I think the more complicated the math becomes.
I think the principle that the existing building is the greenest building is also a really solid one.
So we're taking the hospital down.
We're taking some of the hospital down. Much of the hospital site is still staying there. The pavilion and the Brenton building and the parking lot will remain. The concrete structures will remain. The steel ones we're hoping to deconstruct.
What do you think?
We're all hoping you don't put any city employees in the building.
What's that?
And we're all hoping you don't put any city employees in the building.
I'm not in charge of
Let's use it for
programming.
housing.
So what do you think the potential is for regulations that, real broadly, want people to incorporate some sort of reuse? That's what they're doing in League 4.1. Not necessarily dictating how much materials are reused, but that you just incorporate some reuse after site. Think that's real feasible in the near future for Boulder?
To the extent that we can, we already do some of that. We incentivize using certification programs like LEED as a method of code compliance, and when they do that, then they start to get credit for that sort of thing.
So we'll respect the time of our speakers. We're going to wrap it up. If they want to hang out, you want to talk to them, feel free. There's lots of good resources in this room, obviously, so feel free to chat with each other. There's people who are doing passive house with no foam. There are foam-free system things going on around the room, so feel free to talk amongst yourselves. But just want to thank speakers. Yes.
I did extend the room for another hour, so if you guys want to stay and talk.
Well, let's keep it going.
We got to get back to work. Let them do what they want to do. If y'all want to hang out, feel free. Just a quick round of applause for our